Hi, everyone, once again. And reminding you to, question. So this is in the hands of Leonard Y., the TA. So whatever, I leave him independent on this, so he's the one to ask. But I know he had projects, big projects due today, so I imagine he'll start getting on the case over the weekend. Now, the tournament, we've got 12 entries so far, but I assume lots of you are waiting for the last minute. You can continue to refine your machine players to perfection over the weekend, and I suggest that you try to submit them if you want to compete by Sunday night. We will try to take machine players right up to the last minute, but I can't guarantee exactly how late we'll be able to do that. Yeah, question? Pardon? Oh, there's a whole web page on how to submit your machine player, which is linked off the class web page. So you have to take your project too and change it a little bit, because we can't have everybody's machine player having the same package name. So you have to put it into a package named after your team or your submitter. But once you've done that, it's relatively simple, and the instructions are all online. Question? Come again?
What's the speed of the cube machine?
The cube machine, it is, well, I don't know if it's faster. What I do know is that it's reserved for the tournament. This is the machine we will be running the tournament on. Right now, it's available for CS61B logins only. And so you guys can use that machine now to figure out whether or not your machine player runs within the 5-second time limit. And so I encourage you to do that, but I also encourage you not to run anything else on cube.cs except timing runs with your machine player. So please don't run Emacs on Cube or any other programs or even the compiler. Please try to just restrict Cube to be for doing timings of your machine player to make sure it returns moves always within 5 seconds. And then you'll know whether you're ready for the tournament or not, because we're running the tournament on the same machine. So instructional computing has reserved that machine specially for us. And nobody from outside 61B should be able to log in. The final exam, once again, please make sure you've got it recorded so you don't miss it. It's coming up a weekend from now on Saturday, December 16th. Sadly, it starts at 8 a.m. It'll be in 2050 Valley Life Sciences building. For students who are in the Disabled Students Program and have requested extra time, your exam will start at the same time. It'll probably be in 508 Soda. We don't actually have the room officially reserved yet, but the odds of someone else having reserved it already on a Saturday morning are close to nil, so I think it's pretty safe. It'll probably be there. And if not, please check the web page for updates next week. There will be a review session again, but the TAs in charge haven't gotten organized yet. They're still struggling with classes themselves. There are review questions that I've posted online now, and you'll find them linked from near the top of the class webpage. And so these will give you some practice. And the solutions for these questions, I'll make them available about 48 hours before the exam. Any questions on that? So the first thing I'm going to do today is finish up garbage collection. I talked about two types of garbage collectors last time, the mark and sweep garbage collectors and the copying garbage collectors. And today I'm going to talk about another kind which in the implementation I'm going to describe to you actually uses both mark and sweep and copying garbage collectors inside it as well. It's called a generational garbage collector. Now, generational garbage collectors were inspired by the fact that researchers noticed that when they did studies of memory allocation in a large number of large applications, they found that most objects have short lifetimes. In the majority of programs, most objects are created, live short, brutal lives, and die young. But there are a few lucky ones that go on to live a very long time. And as a general rule, objects are very different from, say, human beings in that the longer they live, the more likely they are to live even longer. So once an object has lived for a certain long period of time, you start to suspect that the program is going to keep that object for a really long time, maybe even the lifetime of the program. And so this observation inspired generational garbage collection, which separates the young objects from the old ones and treats them in different ways. So a generational garbage collector has 2 or more generations. And those generations can be different sizes, and typically are very different sizes. And they can change size during the execution of a program. Because one thing you can't predict in advance is what proportion of the objects that you have to store in memory will be the old ones, and what proportion will be the young ones. And so you have to adjust to that adaptively as your program runs. Now, here's what the Sun JVM looks like. Let's suppose this entire board is memory. This whole blackboard is memory. So the first differentiation is that there's a very big difference between the old generation, which I'll draw up top, and the young generation. The latter usually being larger, but more transient. And so the old generation are basically objects that have been around a long time. And one of the properties of old objects is that they tend not to change very much. And because, like I said, they've lived a long time, chances are they're going to live a lot longer. So you want to keep them as compact as possible. And since they don't die very often, it's easy to do that with a mark and sweep garbage collector. Now, you'll recall that mark and sweep garbage collectors are slower than copying garbage collectors, but because the old objects don't change very much, this garbage collector doesn't have to get run very often. We run it relatively infrequently. And so it's better to use a garbage collector that gives you the best compactness and uses the least memory rather than using the fastest one. When you go to the young generation, the incentives are reversed. It's more important to have fast garbage collection because objects are being born and dying so quickly. And it's not as important to have them be really compact because most of them, well, die so quickly anyway that it's not going to make much of a difference. Now, the young generation, you could actually think of it as being 2 generations itself. So there's sort of a middle-aged generation. Here. And at the very bottom, we have kind of a big open space, which the Sun JVM designers call Eden. Now, Eden is a place where all objects are born, and most of them die. But I'm sure that they have very nice, brutal, short lives there. Every now and then, so Eden is just, to make Eden fast, Eden is just a grab bag of memory. When something needs to be allocated, it's grabbed. And when something gets deallocated, you may not even bother to free up the memory right away. Instead, the JVM just waits until Eden gets full. And when Eden gets full, anything that's left surviving in Eden moves up. So when Eden fills, live objects move up and the places they move up into are called the survivor spaces. And there are two of them. And so when Eden fills up, anything that's left alive in Eden gets to move up into a survivor space. And then Eden just gets cleared out completely, and you start allocating things in there from scratch. So that makes Eden super fast. Now, the two survivor spaces are nothing more than the two halves of a copying garbage collector. And the copying garbage collector starts off at a reasonably small size, and then it expands as necessary if a lot of objects make it out of Eden. Now, when an object gets copied back and forth between a survivor space, you count how many times it's survived through successive copying garbage collection runs. And if an object has lived long enough in the survivor space, it's been through a certain number of garbage collection runs and survived them all, then it gets what's called tenure. So all the old objects get tenured. Do a lot of running around before they get that, but eventually they get up to the old generation, and then they can just, sit down and never move again. Now there's one more problem. Well, there's a problem with this arrangement that's not obvious, which is that to make this work, we want to run the copying garbage collector frequently, because there's a lot of tumult going on in the survivor space, objects dying, new objects moving up. So the copying GC runs frequently. But the old generation doesn't change very quickly, so to save time, we garbage collect it infrequently. And so one of the questions that arises is, well, there's a problem with doing this either kind of garbage collection if you want to do some objects more than the other objects. And the reason is because you might have objects in the old generation pointing down to objects in the survivor space or into Eden. And if that's the case, well, the reason that's a problem is, suppose there's an object here, it's got a pointer to some object here. When you do garbage collection, copying garbage collection here in the survivor space, you only want to do depth-first search on the survivor space. You don't want to have to do garbage collection on the old generation, because you're trying to save time. But if something in the old generation points down to an object in the young generation, and that's the only reference to that object, how are you going to find it? How are you going to know that this object is still live? Well, you better not garbage collect it by accident, or you wreck your program. So basically, the garbage collector has to keep track of pointers from the old generation to the young generation. In a separate table. And that sounds expensive, but the good news is that old objects are so set in their ways, they just don't change very often. So they don't point to the young generation very often. And so usually in the vast majority of programs, there are not a lot of this references, and it's economical to do this. And then once you've got those references, you add them to the roots. Of the copying garbage collector. That collects the dead objects in the survivor spaces. So, any questions about that? I'm going to change topics now. The final topic of our semester is a few thoughts on the idea of augmenting data structures. So once you've got the data structures we've learned in this class, there's lots of ways that you can add things to them to make them do extra little tricks or to run a little faster. So you've done things like this in Project 3, where, for instance, you have the problem where you want something that acts like, well, here's a slightly different problem. You want something that acts like a balanced search tree. In other words, it works like an ordered dictionary, but you want to do lookup in order one time. So I taught data structures that give you all of the operations in logarithmic time, like 2, 3, 4 trees and splay trees. But none of them gives you big O of 1 find time. How do you get a data structure that gives you constant time find operation and all of the ordered dictionary operations that we've come to take for granted in logarithmic time? Anybody know the answer to this? Yeah, add a hash table. So the solution is don't just use one data structure, use two. Use a 2, 3, 4 tree or a splay tree. And use a hash table at the same time. So now the constants go up a little bit because when you store a new item, you're storing it in the splay tree and you're storing it in the hash table. But when you want to look up the item, you only look it up in the hash table, and that gives you order 1 find time. If you want to do any of the other operations, insert, delete, et cetera, or inexact find, like find the number bigger than n that's smallest, then you can still do those things using the balanced search tree in log n time. So there's lots of simple ways to combine data structures like this. In Project 3, you built a graph by combining hash tables and linked lists. And there's a similar question I asked on a final exam once. And this is one of the most common sort of programming ideas that you use in practice. It's not just in Project 3, but it's just the general idea of how do you remove things from lists when they're in lots of different lists at the same time. So suppose you have a database of employee records. And this database has many lists so that you can enumerate all of the employees who have certain properties. Like, for instance, maybe you have a linked list of all of the Prius owners in your company. And maybe you have a list of all of the employees who you've learned by your security cameras in their homes that they're pot smokers. And you can categorize your employees however you like. Okay, now suppose one day you're the boss, you roll into the office, and you just decide at that very moment that you want to fire all the Prius owners because you're sick of watching them hug trees. And here's the trick. You want to fire them all in order S time, where S is the number of Prius owners. Well, of course, you have a list of Prius owners, and this list has length S. So that would seem to be a pretty easy situation, except for the fact that you need to remove them from all of the lists and not just the prius owner's list. And so the solution to doing that, you've probably figured this out from Project 3, is that every database record, every employee who may be on many different lists, so this is an employee database record and has lots of lists pointing to it, every employee just needs to keep a pointer back to all of the list nodes that point to it. So the employee knows that these are the list nodes that refer to it. And assuming there are only a constant number of lists, the employee can remove itself from a constant number of lists in constant time because it knows where those list nodes are. This is presuming they're doubly linked lists, mind you. I guess I should have mentioned that sooner. And so that's a really simple example. I want to give you a more technically interesting example now. But before I do, any questions about that? Okay. A more interesting example is giving splay trees extra node information. There's a number of reasons we'd want to do that, but to give you one example, ultimately we're going to solve the problem of, suppose I want to know how many nodes there are in my tree, or how many items there are in my tree whose key is between 1,000 and 2,000. And I don't want to have to count them all, because that's expensive. If there might be 1,000 or more keys in that range, I just want to figure it out in logarithmic time, what the count is of nodes between 1,000 and 2,000. So let's look at one way to do that. The first idea is that we can record things like the size and height of each subtree at each node. So every tree node is going to have two new fields, a size field and a height field, which tells you the number of nodes in that subtree and the height of that subtree that's rooted at that node. Once you got that, well, how are you going to maintain these lists as you make changes to the tree? Well, for a splay tree, you can do it all during rotation operations. Because splay trees, pretty much every operation they do is just a bunch of rotate operations. And if you look at those rotates one at a time, you can figure out how to keep the size and height updated during each rotate. So let's take a look at, suppose you have nodes like this. X is a left child of Y, and here are the subtrees. And you recall that all splay tree operations are built out of this rotate right operation. And its inverse operation, which is a rotate left. Well, let's look at how to update the height and size of all the nodes after you do a rotation operation. First of all, I'm going to update Y so that we have the new information about Y. And the size of Y, or the size of Y's subtree, is just 1 plus the sum of the sizes of its children's subtrees. And the same is true of X. Once you've computed Y's size, you can compute X's size the same way. And so after you do the rotation, you just update those two numbers with those formulas. at the same time, you can update the height. So the height of y becomes 1 plus the maximum of its two children's heights. And same goes for x. So those are the formulas for updating those two nodes. Now, you don't have to worry about the subtrees because the sizes of these three subtrees and the heights of these three subtrees, A, B, and C, are not changed by the rotation. The subtrees at x and y are obviously changed by this rotation, but also the sizes of all their ancestors are changed as well. So we need to deal with the sizes of their ancestors and get those updated as well at some point. At least for the height. Their sizes don't change, but their heights do. But this is going to work out because when you do a splaying operation, when you do any operation in a splay tree, you take whatever in one of the nodes that you're rotating and you splay it all the way to the top of the tree. So as we splay that node up to the top of the tree, the ancestors of that node are going to get fixed up by subsequent rotation operations. So that pretty much solves the problem for a find operation. If you do an insert operation, it's the same thing because an inserted item gets splayed to the top too. And what about the delete operation? Well, when we do a delete operation, we delete some node in the tree. And so whatever the node we delete is, all of its ancestors are going to have their sizes and their heights change. So we need to go and fix those up. But fortunately, the parent of the deleted node gets splayed to the root. So for all three kinds of operations, find, insert, and delete, you're going to have all the nodes that have their subtrees changed updated so that they have the new correct size and the new correct height. So any questions on that? So here's an example of that. What I'm going to do is I'm going to draw a tree, but at every node I'm not going to draw the key of the splay tree. I'm going to draw the size of the subtree. So this is going to be a tree, a splay tree with 10 nodes. That's the root. 1 over here and 8 in this subtree. And what I'm trying to show here is I'm inserting a new node right here. And all the other nodes have their sizes set to these numbers. Since I'm just adding this new node now, none of those sizes reflect this new node. They don't include that new node yet. So I want to make sure they all get updated. But I also need to do all my zigging and zagging of the splay tree rules. So the first zig is going to be like this. Starts the same at the top, but so what's happened is you can see that I did a rotate through the grandparent, and when I did that rotation, these two nodes had to have their size fields recomputed. And so we just recompute them by adding the children and then adding one to count yourself. And we will continue the zig-zig operation. And so now the item I've splayed has moved one more rotation up the tree, this time rotating through the parent. And we've updated these two nodes again with their new size field. And I'll just do two operations now. The next step is you do a zigzag splay. And one last zig operation at the end. And so what you'll notice here is that when we first added the new node, well, all of the ancestors of that node just had their subtrees get bigger by 1. And none of these numbers on this path up to the root reflect the new node. But we start splaying this new node up the tree, and with every step of the splay operation, the node that we're splaying and all of its descendants will always have the correct size and height fields. The ascendants might not, but those will get fixed eventually, because when our node gets to the root, all of its descendants now have the correct sizes and heights. So any questions about that? In the front, please. How I update the sizes is, let's look at this first rotation right here. So we've done a rotate left. So now this one and this one, they have to be updated. And the way I update this one is I just add the two children's sizes and then add 1 to count itself. So that's 3. And then for this one, I add its two children. 3 plus 1 is 4. And then 1 for itself is 5. Question? Still?
Yeah. When you say deleting nodes and the same to root,
Uh-huh.
one of the things I was under the impression that it was actually the parent of the minimum right child.
If that's the node that gets deleted, yes. So we're not talking about the key that we're deleting. We're talking about the node that we're deleting, which are two different things a lot of the time. Other questions? All right. So now that we've got this, how are we going to use it? Well, I said I wanted to address the following query. How many keys are there? Between some number x and some other number y. So I want to be able to address that query. And I want to do it in n log n amortized time. So here's how you do that. First of all, you do a search for x. So once you find x, you splay it as usual. Or if you don't find it, you splay the node where the search ends to the root. Once you've done that, you'll get a tree that looks something like this. So maybe I've just searched for the number 7, and 7 isn't actually in the tree, so I get a tree that looks something like this. Okay, what I've drawn at the bottom is as well as 4 subtrees. And for those 4 subtrees, the numbers I put inside those subtrees is their sizes. So this is a subtree that has 18 items in it. And we know it has 18 items in it because the root node of this subtree records the fact that its size is 18. And so that means we don't have to go through that subtree and count all 18 items to know that there are 18 items in there. We just look up the number from the root of the subtree, and that's as much as we have to look at that subtree to solve this query. And so the rest of the algorithm is search for y. The other end of the query range. And in this particular case, we want to query the numbers 7 through 75. So in this case, I'll walk all the way to this node here. 85 might have a right child, but I don't care what it is. So I start at the root, and I walk over all of these keys until I reach the 75. And as I'm walking down through those keys, I count how many of them are between 7 and 75. Between x and y in general. And while you're doing that, you look at all of the subtrees to the left of that search path, except for one. You do not look at this subtree here. That one you can forget about. Don't count that one, but count all the other ones. And that's the algorithm. So in this example right here, if I want to know the number of keys between 7 and 75 inclusive, well, there are 5 on the search path that are in that range. Plus, we add in the 4 subtrees to the left of the search path. And that gives us the total number, 33, and it gives it to us in log n time, where n's the size of the tree. And then the final step is, well, we just did a search for y, so we have to display it to the root as usual. So that the tree doesn't remain too deep if it's deep. Any questions? Yeah.
So you can't use a normal, find to the second find. You need to correct all these numbers.
That's true. You do have to change your find operation a little bit.
So why do you have to display after you find y?
Well, suppose I do the same operation over and over again. I say, give me all the keys between 7 and 75, and then I repeat that operation a million times. And this key, 75, just happens to be super deep because the display tree just happened to be super unbalanced at the moment I chose to do that operation. I still have to make sure that every time I do any operation that searches deeply on the display tree, that I balance the display tree after going too deep. Yeah? Well, so all of the numbers in this subtree are less than 73, so that means they're in the range from above. And they're greater than, well, I did a search for 7 here, so they're greater than 7, basically, greater than or equal to 7. So I know that all these subtrees are keys that are between 7 and 75, so I can just count them and know that they're in range. Say that again? Oh, well, I counted 5 numbers on the search path between 7 and 75. So 53 and 57 did get counted. Right, right. But 85 doesn't get counted because it's not less than 75. So I have to check each number on this search path because some of them are bigger than 75 and some of them are smaller. Question? Hey, that might work. That's a good idea. His idea was search for x, splay it to the root, count how many things are in the left subtree, search for y, splay it to the root, count how many things are in the left subtree again, subtract the first one from the second one. I think I'll teach that next time. That's great. Other questions? Well, I wouldn't take credit for it. There's like 100 variants of it, and this is probably the one that came out of my head that night. But lots of people have done lots of stuff like this before, so. All right. Is Eta Kappa Nu in the house? Yeah, so Eta Kappa Nu wants you guys to take a pop quiz. And that'll be your last duty until the final exam. I have one request about these things, which is that it's nice to get really specific advice, which is something I very rarely get. Like, if there was a particular homework that you thought was a waste of your time, or if there was a particular subject that you wish I had covered, it's great to hear about that kind of stuff. If you thought that it would have been better to program splay trees than 2, 3, 4 trees, say that. If you thought I should have given all my lectures in iambic pentameter, well, at least it's specific advice. I once got advice on one of these forums from someone, and what they said was, never ever again wear the brown jacket with jeans. And When I tell people that story, often they think that that's a mean or inappropriate comment, but it's actually the most useful specific advice I ever got, and I implemented it immediately. And one final thought before I go. I heard the president on the radio this morning. He's announcing a new, improved American English plan so that all of those important American words that are so difficult to spell are now easier to spell than ever. And so as of today, by presidential decree, the word abysmal is spelt G-R-E-A-T. So please remember that when you're filling out your evaluation forms. You'll find that with this new plan, you can write down abysmal 20 or 30 times.